All right, great. All right, well, welcome everyone to our November Geodesy Early Career webinar. We're so pleased today to have our section president with us today. Annie Kazanave is here, as well as our speaker, who is Dr. Susanna Ebmeyer. Uh, Dr. Ebmeyer received her undergraduate degree from the University of Edinburgh and her doctorate from the University of Oxford. She served as a European Space Agency Fellow and a postdoc at the University of Bristol, and is currently a NERC Independent Research Fellow at the University of Leeds. And we are also pleased to welcome her as one of the co-recipients of the 2022 AGU Geodesy Early Career Awards named after John Warr. And so for all these reasons, we're so excited to have Susie here to talk to us about some science. Just so you know, I will turn off the chat and mute everyone during the seminar. And so please save your questions for the end. And with that, I guess we will get started. Go ahead, Susie.
Hi, thank you, Matt. Can you hear me?
Yes.
Okay, good. It's the last time I'm going to ask that. It's always this temptation to keep checking during an online presentation. Okay, thank you very much for the invitation to speak to you today. And I've taken the chance to talk about quite a range of different things. So you can probably tell that from my title. I've got measurements of lava extrusion and also the dynamics of magma supply. So I'm kind of going from one end to the other end of the scale of what we can reasonably measure with SAR. So my research is primarily focused on how to use satellite radar, so synthetic aperture radar, to understand volcanic processes. So that involves questions about how we can monitor volcanoes better, how to interpret global data sets, which is something that I've been working on since my PhD, when I first did kind of regional scale studies of Central American volcanoes within SAR, and what we can understand about magma storage from looking at volcanic deformation measurements. So I think that the kind of general theme of this seminar is going to be extracting new types of volcanologically useful information from SAR, and I'm particularly interested in exploring ways to do that are novel, that haven't been tried before, and seeing if we can really make the most of these data sets, both for kind of science questions and for practical monitoring questions. So I've divided the talk up into three rough sections. So first, I'm going to talk a little bit about the implications of relatively recently available global open data sets, so particularly Sentinel-1, which a lot of our energy here at Leeds has been devoted to studying over the past 5 years since I've been here. So I'm going to talk a little bit about automated processing of volcanology, when it works, when it doesn't work, and some different approaches for machine learning. And then I'm going to talk about two fairly different case studies, but I suppose they're linked by trying to improve on the methods that we already use to learn things about volcanic systems from SAR data. So one is in the Western Galapagos. So that's looking at variations in magma flux through the Galapagos Islands themselves, and particularly trying to see what we can understand from looking at correlations and time series of different volcanoes there. And the other one is focused on eruption dynamics from SAR backscatter. So it's a few different case studies, and it's really trying to understand what we can learn from applying some corrections and from trying to understand the processes involved in the way that radar interacts with new volcanic products on the ground. So I'm going to start off kind of zoomed out, relatively big picture, talking about global data sets, and then I'm going to focus in on a few case studies. So one of the things that we've been working on as part of COMET in the UK and particularly in Leeds, where there's a lot of effort gone into kind of automating processing of Sentinel-1 imagery, is it's called the LIXARS, Looking at Continents from Space processor. So the aim here, which is pretty ambitious, was always to process all of the Sentinel-1 data available for all of the tectonic and volcanically active regions in the world. And that's given us an awful lot of data, which we need to work quite hard, I guess, to try and maximize our interpretation of. So the map on the bottom right there currently shows all of the volcanoes for which we have some interferograms processed, with the color scale representing the number of interferograms per frame. And you can see it's fairly patchy in different parts of the world, which depends a little bit on data density and also the kind of emphasis of different research projects. And something that I've been working on, particularly in collaboration with Juliet Biggs in Bristol, is sets of online tools which allow people to use these data kind of immediately. So the ethos behind that is that the tools should be open. They should allow scientists to interrogate the INSAR data themselves and test whether it's reliable and useful. It shouldn't require any local processing for anyone. You don't have to download it onto your own machine. And it allows you to do a little bit of on-the-fly analysis online. And it's really targeted quite specifically at regions tens of kilometers around volcanoes. So the aim here is that it's for volcano observatory scientists to have a first look at some data, decide whether it might be useful, and make some comparisons to their own ground-based data sets or perhaps to local processing. So the tools on the website look something like this. So this is an example from Fernandina, which always produces really beautiful displacement signals. And you can see we've got multiple different frames you can look at. You can apply atmospheric corrections. You can look at filtered and unfiltered time series, use a slider to flick through different interferograms, and really just interrogate the interferograms yourself. And the ethos here was always that we should allow people to judge the quality of the data themselves rather than putting a kind of like a gold standard interpretation online. So there are tools on there that allow people to assess individual interferograms, look at the relationship of a phase signal to topography, check whether it's associated with multiple look directions and multiple acquisitions. You can do things like make profiles through topography and phase and compare them. You can identify seasonal trends and remove them, as well as applying some weather model-based atmospheric corrections. And you can play around with things like reference pixel and looking at whether the signal is correlated with land cover. So there's quite a lot you can do on there, and I think there's quite a lot of very valuable insights you can get already from looking at the data like that. But it really works well only for a particular subset of volcanic signals. So first of all, those that are higher magnitude, as in there's a very large displacement in a single interferogram, and also high rates of more than a few centimeters a year. And it really only works very well at the moment in very coherent areas, and particularly areas where there aren't major seasonal variations in coherence. So it doesn't work quite so well where you have seasonal snow cover, for example. So there are things that we can do to improve on these results. And you can get really, I think, quite surprising insights by processing the data with a little bit more attention to the resolution, doing some iterative unwrapping, manually looking at the quality of the unwrapping and adjusting it, and particularly tailoring the network design to avoid any fading signal, which is this sort of effect that we seem to get when you have a network which is largely composed of short duration interferograms, perhaps containing contributions from things like soil moisture, perhaps containing contributions from lots of unwrapping errors that we're not necessarily picking up. The net effect of which is that you have a long-term trend which appears in the data set. And that does affect some of our data in the portal at the moment. And the other thing that I want to make the case that we can always do more is we can exploit other satellites, we can look at other wavelengths and look at results from instruments with other acquisition strategies. So I'm going to talk very briefly about the Committee for Earth Observation Satellites Volcano Demonstrator, whose aim is to try and make those kind of data sets more available. So first, I'm going to go to a couple of case studies that show what you can do beyond automated processing. So this is from Central Chile. It's work by Fei Liu, who's a PhD student at the University of Leeds. And Fei's PhD project was actually to try and look at small earthquakes and look at detection thresholds for relatively deep earthquakes. So he was interested in this event here. And when he processed the data over this region, he noticed something interesting, which was that Socompa volcano, which doesn't have a record of historical activity, although it does have active hydrothermal systems and has been a target for kind of geothermal exploration recently, seemed to start uplifting at a similar time to the earthquake that he was studying took place. And we've been very fortunate in being able to confirm this by comparing phase INSAR measurements to GPS measurements from a station that was installed as part of a project that Matt was running. And I think Scott Henderson was also involved in the installation. And Francisco Delgado, who's also on the call here, picked up the data from this GPS station earlier in the year and allowed us to make a comparison. And what that showed us was that actually it looks most likely that the uplift at Sacompa started a little bit in advance of this relatively deep earthquake. So we've not really got any basis for thinking the two events were correlated, but nevertheless, the Sacompa uplift is, I think, a really interesting observation. It seems to be originating at a geodetic source of about 6 kilometers depth, which is an oblate spheroid, and it's which is a similar depth to the source at Lastaria to the south, but a little bit different to the other volcanoes in a similar region. And it's at a rate which wasn't detectable with our automatic processing. It's not that slow, it's about 1.8 centimeters a year, and it's been fairly persistent since 2019 when it started. But it's not immediately apparent when you look at the portal results. And the same thing could be said for Sangay in Ecuador, which is where Pedro Espin-Bedon has been working. So Pedro is an IG scientist from Instituto Geofísico in Ecuador, and he's also doing a PhD at Leeds. And when we first looked at the automatic results for Sangay, they looked really exciting. We've got this really major uplift event happening here, in spite of the fact that coherence is relatively poor. But the more that we dug into this and tried to really interrogate this signal, the less convinced we became by it. And eventually, what we determined was that if you remove the short timescale interferograms, you actually remove a lot of this long-term uplift signal. But thankfully for Pedro's research, not all of it. And you're left with something which is much more reliable and much more interesting. So you have cumulative displacements, which end up being smaller than was initially looked like it would be from the automatic processing. But they tell a really interesting story. So in this case, you can see the ascending and descending results have this kind of strange relationship, which we think at the moment is most likely to be consistent with a leaning, vertically elongated spheroid, illustrated by this cartoon here. But you've got two sort of overprinted signals on top of that. So the bottom panel here shows some cross sections across the across Sangay volcano. So that's the height scale and length, the height and width scale there are 1-to-1. So the vectors actually represent the direction of motion. And we've got a zone here in the green box where you have almost slope parallel motion, which we attribute to shallow sliding related to the recently in place deposits in one of the quebradas, and then a kind of similar smaller feature on the northwest flank of the volcano. And these signals were all relatively low magnitude and actually masked by the noise and the artifacts that came through the automatically processed data. So they required quite a lot of additional effort to get at, but they do tell a really interesting story. So one of the methods that Pedro was able to use to identify the shallow deformation features at Sangay was by looking at the high resolution X-band data to find offsets in the fringes. And that was something that was provided through the Committee for Earth Observation Satellites Volcano Demonstrator Project. So that's been something that's been running in various forms for a while, and it's had a couple of transformations. So initially there was a pilot project in Latin America from 2014 to 2017. It involved a lot of volcano observatory scientists and a lot of international collaborations. And I think it really demonstrated the utility of bringing together multiple different types of satellite imagery. So since 2019, I've been leading the volcano demonstrator, which is kind of the inheritor from the pilot, along with Mike Poland at the USGS. And one of the big tasks that we had, which was kind of requested from the space agencies, was that we expanded from looking at the Latin American test case to other parts of the world. So to Africa and to Southeast Asia in particular. And that was meant to run for 3 years. We've now had a COVID extension, so it's keeping going until the middle of next year at least. And we're working on coming up with a sustainable future for this project. In very practical terms, what it allows us to do is provide a route for volcano observatory scientists and for researchers to get access to high resolution imagery from commercial or semi-commercial providers. And the big goal is essentially to demonstrate that it's necessary and also possible to coordinate tasking for volcanic acquisitions internationally between different space agencies and for different missions. And one of the ideas that's been proposed is that we kind of move to a new model, which is a virtual volcano observatory from next year onwards, which should have a similar setup as, and it'd be quotas from each of the space agencies, but it would also perhaps allow us to have a kind of separate quota for background research and monitoring versus response to different events, and perhaps extend geographically from these regions. So during the demonstrator period, the yellow dots on this map represent events that we've responded to. So either where CEOS data set, so that's generally TerraSAR-X, Cosmos, SkyMed, or Pleiad imagery, is being used for monitoring or for event response, so during unrest or eruption. And the case that we always make to the space agencies from looking at this data is that we can do things with it that aren't possible with a freely available data set. So it's important that the provision continues. And that while the global data sets, such as Sentinel, that I've been talking about so far, are important for baseline monitoring, the constellation approach to SAR is critical for responding to specific unrest and eruption events, just because you potentially get a lower latency between event acquisitions, and also higher resolution allows you to look at events close to volcanic vents and localized deformation signals, which are potentially very important. The one thing that you can do with the global data sets, which is not really possible with the more ad hoc acquisitions, is applying machine learning methods. And this is something there's been a lot of work on in the last few years by many different groups. So I'll draw your attention to the work from Bristol, which is implemented on the Comet Volcano portal here. It's led by Juliette Biggs, and it's highlighted in pink there. So you can see high magnitude displacements are detected automatically on the Comet portal. And there's a table there of recent activity, which you can look at on the front page. So that uses convolutional neural networks trained on volcanic signals. And there's other approaches to trying to detect volcanic deformation in SAR. For example, use of blind source separation methods. And I think there's probably quite a lot of work you could still do in this area. So one of the things that I think is quite exciting as a possibility is, instead of trying to identify volcanic deformation based on an understanding of what it looks like, is identifying it as an anomaly. So I want to talk briefly about Anza Shakil's work. So Anza just finished her PhD a couple of months ago and passed her Viva. And what she has developed is it's an autoencoder long short-term memory-based anomaly detector for INSAR. So what's different about this to a lot of the previous work on machine learning is that instead of being based on training data sets where volcanic deformation or magmatic deformation has been identified by an expert, instead it's trained on normal interferograms. So all it really does is it takes the normal interferograms and it predicts from them what the epoch images, so the individual acquisitions, should look like, using the redundancy in the network of interferograms. So if you've got this right and you've not included any deformation in the training data set, it should essentially take the relationship between atmospheric contributions or orbital uncertainties, for example, and provide you with a rigorous way to convert from epoch images to interferograms. Excuse me. So the nice thing about that is that if there is any deformation in any of the interferograms that go into your classification data set, they can be pulled out as an anomaly. So that would be the case for this panel on the bottom right here, where you have some kind of deformation signal apparent in some of the interferograms, and it translates into a signal in the epoch images. So Anza's developed a new architecture, which is essentially based on this idea. It's the kind of the unique structure of differential INSAR data. And as tested on some synthetic data, it looks like it has a detection accuracy of about 80 to 90% for deformation of the order of about a centimeter, although that's quite a hard thing to test. So at the moment, this has not been applied very widely to different data sets, It was trained on a data set from northern Turkey. So Amza started her PhD, she was working with Richard Walters, who has a particular interest in that area. And more recently, we've taken it and applied it to classify data in southern Turkey and in Argentina. And I think what's really cool about this is it actually works relatively well, because all it depends upon is this relationship between atmosphere in an epoch and atmosphere in a set of interferograms, rather than any of the particular properties of the atmosphere in a place itself. So the other neat thing that Amza's work does is it uses a redundancy in interferogram networks to get temporally consistent identification of anomalies. So she can say whether an anomaly appears in one epoch on the basis of several different data batches, depending on where that epoch appears. So this is a kind of schematic indication of what one data batch and then the next one looks like in a sequence. So to show you how this seems to work, this is what our initial tests show. So she has she's used this on an earthquake in southern Turkey. And I think the clearest panel to focus on here is this central one, where you can look at the interferogram number, the temporal span of the interferograms, and the earthquake occurred here in this red area. And you can see that all of the interferograms that spanned it and none that didn't were flagged as detecting an anomalous signal. You can also kind of reconstruct the spatial structure of the detected earthquake relatively well. And although that's satisfying that works, it's not particularly impressive, because this is a sort of signal that you can pull out of the image just by looking at it yourself. So the next case study that we've tested it on is from Demullo volcano in Argentina. Now, the deformation at Demullo is very, very clear in a time series. But if you look at the individual interferograms, the signal to noise ratio for those is shown here in this central plot. And you can see that the dotted line in the middle there is 1. Most of them, the signal to noise ratio is relatively low. And we also haven't done any sort of quality control on the data that went into Amza's modeling here. We've chucked in all the data that had gaps in it, where it had poor coherence. We haven't designed a specific network. This is essentially just taking what had been automatically processed and what was available on the basis of a processing scheme that was designed for tectonic applications. But the nice thing is that every single interferogram in this network was flagged as containing deformation, because it didn't fit the predictions of how atmosphere would behave when you just try and reconstruct it from the interferograms themselves. And it allowed us to reconstruct an accumulated displacement field, which matches a stack relatively well. So at this point, I think you could get a very similar result by doing a time series analysis. But the neat thing about this is that it could be applied to any individual interferogram without having the full data set. So I think the potential is that you wouldn't need to wait until you had enough interferograms to build a stack with a high signal to noise ratio, or to produce a time series, take a time series approach to analysis. You could essentially use this method just to say whether there was an anomalous signal in individual interferograms that might potentially be deformation. So I think it has some potential for development in the future. Okay, so I'm going to move on to the next segment now. I'm just going to check the time. Okay, I think we're doing all right. So this is a slightly different change of pace. I'm going to focus more on one particular project, which is by a PhD student, Owen Redding, who I've been working with for, I think, 4 years now. So he's coming up to writing up his thesis. And he's been looking at geodetic evidence for magmatic connectivity in the Galapagos. So the Galapagos is a really nice place to look at INSAR data, first because it's really coherent, and second because you have exceptionally high rates of volcanic eruptions, intrusions, and very high magnitude displacements. And one of the things that we've been interested in is trying to understand the distribution of eruptions in the Galapagos Islands through time, whether they're clustered at all or whether they kind of seem to happen at regular intervals. 6 of the volcanoes in the Western Galapagos, there are 6 volcanoes in the Western Galapagos, and 5 of them, so everyone except Darwin, has had multiple eruptions in the 20th century. And if you read about volcanism in the Galapagos, you come across this kind of classification scheme, which is based on volcano maturity, and in turn which is something that's derived from a proxy for magma temperature, the magnesium number from erupted lavas. And this is kind of counterintuitive if you're familiar mostly with looking at the deformation of the Galapagos, because the most active volcanoes in terms of unrest and deformation are probably Sierra Negra and Fernandina. And these are classified as either mature or dying, having very having cooler magmatic systems. So one of the things that we were interested in trying to do with Owen's work was to see if we could see any indication of the differences in magma storage, which is implied by this classification in the type of unrest and the understanding we can get from the geodesy of the magmatic systems in the Galapagos. So I'd like to acknowledge there's been a lot of INSAR work done in the Galapagos before, going all the way back to the 1990s and including some really insightful, interesting recent studies. The majority of that work has really focused on deformation that occurs during eruptive periods or major episodes of unrest, so dike or sill intrusions at particular volcanoes. So it's had a particular recent focus on caldera formations and also on stress interactions. And one thing that we'd like to try and do with this work is focus a little bit more on the background deformation signals that occur during periods of quiescence between major intrusions and between eruptions. So from other people's work, all the volcanoes in the Galapagos seem to have geodetic evidence of shallow reservoirs, so 2 to 3 kilometers depth, and several also have evidence of much larger storage zones at around 5 kilometers. And you also have these kind of subcaldera systems at Sierra Negra and Fernandina. But we're kind of limited in looking beyond that depth to some extent because of the size of the Galapagos Islands themselves. So what we're trying to do here is work out whether the relationship between the displacement you see at different volcanoes can tell us anything about the magma supply into the system and the deeper dynamics. So on the panel on the left, you can see the Sentinel-1 time series for displacement at the 6 volcanoes of the Western Galapagos. And panel A at the top there is just showing you the reference pixel that's been used to construct these time series. So this is for the descending data set. This is for the ascending. You can see they're broadly similar. The difference is largely due to the choice of pixel to plot within calderas where you have trapdoor faulting particularly. You can have quite a different east-west direction of motion, which makes a difference to what it looks like from an ascending or a descending geometry in INSAR. And if you spend any time looking at these time series, there are a few things that jump out at you. So one is the relationship between eruptions and displacements. And then the other, when you dig into it a bit more, is the similarities between these time series. So for example, if I could draw your attention to this period leading up to the 2018 eruption of Sierra Negra, you can see there's similarities in the rate, in the location of the turning points, particularly in the time series at Cerro Azul, Darwin, Fernandina, and Sierra Negra. You can see something similar in the period shortly after that eruption, where you have a turning point occurring at exactly the same time at El Cedo and at Sierra Negra, which if you refer to the map here, they're close, but they're not, they're some distance away. They're not the same magmatic system as far as we know. And finally, there's a particularly exciting example here before the 2022 eruption of Wolf, where you can see in the pre-eruptive period, there are commonalities in the time series. And then you have this turning point that appears just before the eruption at multiple volcanoes. So we're not the first people to have noticed this at the Galapagos or to have pointed it out. So we went back and had a look at Scott Baker's PhD thesis, and Owen looked at the data sets that he's used and where possible applied more recent methods of atmospheric correction and tried to clear them up. And essentially what you can see there is 4 rather distinct episodes of apparent correlation in displacements at different volcanoes in the Galapagos. So you've got an event in 2006, 2007, and then another few which were associated with eruptions at Fernandina and Cerro Azul and unrest at El Cedo. So our first approach to this problem was to say, well, maybe you have particular episodes which are associated with events that result in correlations in the time series. And maybe this is an anomalous behavior that happens now and again at the Galapagos, but isn't taking place all of the time. So we tried to go through and look for similar events in the Sentinel-1 period, where we've got much higher temporal resolution time series. And what we seemed to find wasn't that we had similar clusters of volcanoes with correlations between them, but that actually a lot of the time, all of the volcanoes, in fact, had remarkably similar time series. So we set out to look at this in a little bit more of a systematic way. So first of all was the identification of turning points in the time series, which I think you can see by eye quite clearly just by kind of looking at the data. The second was doing a windowed paired correlation analysis. So the figure here shows all of the possible pairs of Galapagos volcanoes for the ascending and descending Sentinel-1 data sets for the Galapagos. So this is looking at correlations over 3-month windows. Anything with a correlation value of more than 0.9 is plotted as a color in this figure. Red being positive correlation, blue being negative correlation. And you can see immediately that they're mostly positively correlated, except for a few episodes which are associated with eruptive periods. So the pink boxes that I've drawn on here are the same as I showed in the time series a minute ago. So the first one is associated with the 2018 eruption of Sierra Negra. The second is the eruption of Wolf this year. And the final method we used to look at this was temporal independent component analysis. So this was where you take a set of time series here and decompose them on the basis of statistical independence into a spatial pattern, into an independent component through time, and a spatial pattern which represents the strength of that component at every single location around the islands. So first of all, we downsampled the number of time series from our INSAR data set spatially, with a higher sampling rate around the calderas and a lower one in between. And then we applied the temporal ICA to those resulting 8,000 time series to particular time windows, which we identified from the paired correlation analysis. So we looked at the clusters that we retrieved from that using a KME method. And what you can do with that is then look at the spatial pattern of the independent component strength. So to show you what that looks like, this panel on the bottom right here is a temporal component, which was in the run-up to the 2018 eruption of Sierra Negra. That's what it looks like. And this is its strength as it varies around different parts of the Galapagos. And you can see, as we'd expect, it's relatively strong at Sierra Negra and actually at the eruption site here. But it also seems to be very active at Fernandina. And at the other end of the color scale, it's a little bit weaker, but still present at several of the other volcanoes, at Cerro Azul and at Wolf. Similarly, and I think perhaps more convincingly, you can see the same thing going on in this period before the Wolf eruption in 2022. You have a temporal component with a similar shape, and it seems to be active at multiple volcanoes. And this is really robust evidence that that causally related processes are taking place at multiple volcanoes at the same time. So there's a few potential explanations to this. So the first one to rule out is actually what we're looking at is just correlations on the basis of artifacts in our processing, because we've processed the data set in the same way. And we spent some time trying to eliminate that, and we're fairly confident that's not the case. We looked into the possibility that we were being affected by choice of reference pixel and did some systematic testing on that, and it doesn't seem to be the case. And we also checked whether the atmospheric corrections could be introducing some sort of commonality just at the volcanoes. But again, that doesn't seem particularly plausible. The next possibility, which seems an obvious thing to check, is whether these correlations are the result of static stress changes associated with eruption and unrest. So we calculated using using the assumption that the largest eruption, that Sierra Negra 2018 event, would be the most kind of promising candidate for that. And what we found is that even that really, really large event, orders of magnitude larger than anything else that happened in the time period, didn't cause sufficient dilational strain or Coulomb stress changes that we can attribute the unrest at all of the other volcanoes being due to static stress. So another possibility is that you have shallow hydraulic connections between the different volcanoes, but we see no evidence for that geodetically. We don't see, if there was a shallow dike connecting them that changed that had a change in opening, for example, we would expect to see that in the displacement fields, which we don't. And there also isn't evidence from other sources that you have, for example, porous flow connecting the different calderas. Certainly not across all the different volcanoes on the island, because remember, we're not just looking at correlations between neighboring pairs of volcanoes, but volcanoes across the whole of Fernandina and Isabella Islands. So what we're left with is probably the idea that we have deep connections to a common magma supply, and that variations in that supply are responsible for the correlations in the time series. So we looked into that a little bit further, and one of the things we looked at was picking up some work of Marco Bagnardi's. So he was looking at the flux through the Western Galapagos up until around 2010, and we've done something similar for the Sentinel-1 era and compared that to Marco's work. So for people not as familiar with INSAR datasets, the grey bar here is actually a gap in data availability. And what you can see is that, first of all, the intrusive flux varies over decades, and that fits in with what we know about eruptions at the Galapagos, and particularly some of the larger events seem to be driven by flushing events where juvenile material is kind of pushed through the system and causes the eruption. So we don't really expect the intrusive flux to be constant through time. And I think a little bit more intriguingly, you can also see there's a little bit of a variation in the partitioning of magma supply between the different volcanoes over this time period by itself. So if we dig into that idea a little bit more, we looked at the intrusive and extrusive volume change. The intrusive derived from applying analytical models to the geodetic sources that were active during the Sentinel-1 time period and estimating volume changes, and extrusive estimated from volumes of erupted lavas. And we looked at the correlation between those values and the correlation counts, so the number of pairs of volcanoes where you had high correlations during the different time periods. And what we found is that you seem to have higher correlation counts corresponding with episodes of high magma flux. So that kind of makes sense, and it makes sense of the initial correlation analysis that I showed. We have the majority of strong correlations that occur between pairs of displacement time series when they're uplift. So the most common scenario seems to be that there's correlated uplift at multiple systems resulting in a positive correlation. And that seems to happen in most extreme manner when you have episodes of high melt supply. There are also episodes of correlated subsidence, which seem to be associated with periods when the melt supply is a little bit lower. So you can imagine that might happen if shallow reservoirs stop pressurizing because the supply from depth slows down a bit. And then we have a couple of shorter episodes of negative correlation, which affect fewer pairs of volcanoes. And there's two ways that we think you could interpret that. So one could be that you have a change in partitioning at depth in the supply of magma to different parts of the Western Galapagos Islands. And the other possibility is that you have some top-down influence on the magma supply to the shallow reservoirs, which might be associated with for example, with some of the eruptions. So I think the latter is probably our preferred explanation, especially because this negative correlation seems to happen when we have relatively large eruptions like the 2018 event at Sierra Negra. So I think what we can conclude from this is that relationships between displacement at clusters of active volcanoes can provide you with an additional source of information about the connections between them and how they link to the deeper magmatic systems. The Western Galapagos volcanoes themselves consistently over a decade at least experience correlated displacements. We can see that much more clearly in the Sentinel data than you can in the ERS and the NVSAT, just because of the improved temporal resolution of the imagery. And the correlated displacement themselves occur more during periods of heightened magma supply to the shallow crust. And the kind of concluding idea, I guess, is that episodic surges of magma into transcrustal magmatic systems, which are connected at depth, though we can't necessarily say anything about what depth they have a connection, can result in effects at neighboring volcanoes simultaneously, giving you correlations in uplift and in subsidence. Okay, I'm just going to check how I'm doing for time. Okay, I'm going to move on to the last segment, which is going right down from the bottom of a magma supply to a volcanic system to the expression of magma in the volcano itself. So particularly trying to interpret the dynamics of volcanic eruptions from backscatter. So I think backscatter is something that's underused in volcano monitoring because it's a challenging thing to interpret. There's not really a unique interpretation for an increase or a decrease in backscatter. It depends on multiple factors. And this work was led by my first PhD student. She's now a doctor. She just graduated and did all her corrections. So Edna Dawala, who's now working as a postdoc at the University of Bristol. And Edna's PhD was really trying to address this question of how we can make SAR backscatter useful for volcano monitoring and for research. So she thought quite a lot about the different factors that contribute to a backscatter signal in any individual interferogram. So, what she was thinking about particularly is backscatter coefficient and how it's affected by the gradient of local slope, the surface roughness on the length scale of the radar wavelength, and the changes in dielectric constant. And her PhD work was really divided into 3 different case studies. So one at Volcán de Fuego, Guatemala, one at Kilauea in Hawaii, and most recently, La Soufriere St. Vincent, which was work that was in collaboration with the volcano demonstrator using multiple different data sets. So the nice thing about using backscatter, as opposed to, say, optical imagery for mapping out flows and for looking at the impacts of eruptions, of course, that it's not affected by clouds. But the challenging thing is that you have a kind of non-unique response to a particular volcanic event. So, for example, a pyroclastic flow can cause either an increase or a decrease in backscatter, depending on its interaction with the local topography, so how it affects the shape of the channel, and its how it varies in surface roughness relative to the pre-existing surface. So making a good interpretation of backscatter, particularly during an explosive eruption, depends on understanding the properties of the material that was there before and also the change in the local topography. So I think this is a very clear example from the eruption at Fuego in 2018, where you can see these kind of stripy blue and red regions indicate where the channel has been overtopped by a pyroclastic density current. One thing that we found that we're able to do with backscatter, which you can't necessarily do with, for example, making maps of coherence loss caused by volcanic flows, is that you can capture both aspects of the emplacement of a new volcanic deposit and alteration. So typically what you might have is a drop in backscatter when the deposit is initially in place, and then a kind of gradual recovery as it's removed or as it weathers and alters. Which is obviously quite different for an explosive deposit relative to a lava flow, say. So the big challenge at Fuego was really trying to work out how you could detect lahars reliably using SAR backscatter. And that was a much more challenging thing to look at than the pyroclastic flows because they're much more temporally limited, and also they looked in terms of backscatter like an erosion event, which could be caused by heavy rainfall. So the way that Edna tackled this in the end was to produce these matrix plots here, which essentially compare backscatter of a particular part of the channels at Fuego for every possible combination of SAR images that she had available to her. So this is a Cosmos SkyMed data set primarily that she was looking at. And you can see this highlights very clearly when you have a pyroclastic current coming down, but also when you have lahars. And you can see the gradual variation in backscatter recovery that occurs after the emplacement of a new lahar. And we were able to kind of correlate the lahar emplacements with rainfall events to check that we understood what we were detecting. And this worked. It wasn't a kind of a perfect result, but I think it was relatively successful when we compared the lahar detections from the radar backscatter with those from the INSAVUME reports. They more or less captured the same events. Now you can do a little bit more with lava flows because they're matched to some extent by a simpler model of how backscatter changes with time during a lava flow emplacement. So Edna worked a lot on this at the Kilauea data sets, and you can see that backscatter here drops during flow emplacement, and you have a gradual grand recovery. And then the post-lava flow backscatter doesn't quite recover back to the pre-lava flow levels. So that was our basic model, which worked relatively well for identifying some features of the lava flow emplacement from the backscatter. So this is the tandem X difference map produced by Mike Poland. And this is the time to emplacement map that Edna managed to retrieve directly from the backscatter itself. And the neat thing here is that didn't use any information from coherence or any other independent data source. This is just by looking at the radar backscatter itself, which is a part of the data set which is normally treated as it's not normally treated as something that's useful for volcano monitoring for this sort of purpose. So if you look at the animation, you can see the development of the flow just from the backscatter itself. And Edna was able to produce this by solving for this step of a drop-in backscatter associated with flow emplacement. So something else that's been done at several places around the world with backscatter measurements is using shadows to try and retrieve parts of volcanic topography. And that's been done at El Reventador in David Arnold's work, and it's been done at Nyiragongo and at Erta Ale with quite a lot of success. And Edna did some evaluation of this at the Pu'u'u lava lake. And it works here relatively well, but it's highly dependent on the geometry of the crater relative to the lava lake and any assumptions you make about its morphology. So she did I think a really nice test of comparing the crater depths that she got from the radar shadows by themselves to what she could get from looking at the HVO images and HVO reports. And although they agree relatively well most of the time, there are certain kind of transient geometries of the crater that existed during this time period from 2011 to 2013 that weren't really suitable for extracting crater floor heights from the radar shadow. And this, in some respect, is kind of motivation for the work that Edna went on to do at St. Vincent. So the 2021 dome growth event at St. Vincent was captured by TerraSAR-X, Cosmos SkyMed, Sentinel-1, and ALOS imagery. It was a very comprehensive data set that spanned multiple wavelengths and meant that you had images every few days for a period of lava dome growth that lasted for 3.5 months. And the assumption here for most of this work is that the backscatter signal that you can see in the GIF in the bottom left of this slide was primarily a result of changes in slope. And what Edna was able to do was to take lines of range across the backscatter images and integrate them based on the assumption that all of the backscatter difference was caused by changes in topography. So this required some calibration for variations in backscatter levels across the image, which she was able to do by comparison to the values that were present over the 1979 older dome here. And it was also helped by having good pre-eruption digital elevation models, which are derived from Pleiad imagery from Raphael Grandin. And the neat thing that she was able to do here was extract the topography directly from range lines in the SAR image. And this allowed her to reconstruct the shape of the dome for all of the images, for all of the different geometries, almost all the different geometries that spanned the whole period of dome growth. So you can see her final models of what the dome looked like in the bottom panel here. You can see how it grew from a relatively round shape to kind of extended sort of a sausage shape up until April. This map up here shows the elevation, the retrieval of the digital elevation model itself, the difference relative to the pre-dome growth topography, and then her best fit solution for elevation, which involves some spatial smoothing on this triangular mesh grid. And I think this is the really exciting result that you get from that, because you have a completely new source of information about extrusion rate, which doesn't rely on ground-based measurements or structure from motion photogrammetry. So it produces a much denser time series than what was available from the measurements that were being made on the ground at the time. So you can see those ground-based measurements or aerolite measurements are indicated by the black stars here. And all of the other data points come from different SAR geometries. So blue being Sentinel, yellow being TerraSAR-X. And we were particularly fortunate in having a one-day Cosmos SkyNode pair acquired immediately before the transition from a period of dome growth into explosive eruption in April of that year. And I think the really impressive result from this is that you have good evidence for a relatively steady period of extrusion all the way from that initial event back in December until just a couple of days before the explosive eruption itself. And you can see here there was actually a change in extrusion rate by almost an order of magnitude that occurred just over a day before the explosive eruption. So this was obviously a retrospective analysis of a data set that was acquired during the eruption, but this kind of offers the intriguing potential that if you're able to make these measurements during the development of a lava dome eruption, we might have been able to detect that change of an extrusion rate, which also correlated quite clearly with the first detections of SO2, which had given us some idea that perhaps the volcano was going to change its behavior and enter this transition into a much more dangerous explosive event. Okay, I think I'm going to leave some time for questions. I would like to finish by saying thank you for the invitation to talk to you. I'm sorry I won't be at AGU this year, but it'd be great to have questions online and to hear any feedback that anyone has. And also I would like to send a big thank you to my former supervisors. And I've been very lucky in them and also in my current colleagues and my collaborators overseas and students in that I've been supported in doing interesting science. And I've learned from them. And I think that science today is really the result of supportive collaboration. And I know that's really been the case for a lot of my work. So I'd like to acknowledge that. And I hope that it's been clear that throughout a lot of the work that I presented in this talk, a lot of it's come from collaboration with PhD students. So a lot of the credit should also go to them. So thank you. I'll take any questions.
Great. Thank you so much, Susie. I will open up the chat here and open up the ability for people to ask questions and unmute themselves if they wish. Does anyone have a question for Susie right off the bat? If not, I'll take chair's prerogative here and ask you the first question. Oh, go ahead, Annie.
Okay. First of all, thanks very much for this very interesting presentation. I'm not an expert, but really I like it very much. My question is about, I cannot open my camera, but it's okay. My question is about the deep magma connection that you observe at the, I think it's Galapagos volcanoes. My question is, first of all, have you observed this elsewhere at other places, other volcanoes? And I was wondering if it can say something about the intensity of the eruption, if you have the magma distributed below different edifices, maybe the intensity of the eruption will be less than if it were not the case. I don't know. I'm not an expert, but I would like to hear you and comment about that.
Okay, so the first bit was whether I'd observed this in other places, and the answer is not personally. But other people have proposed that you can see something similar going on at Mauna Loa and Kilauea in terms of a common response to deep changes in magma flux. So one of Mike Poland's papers discusses that, and a lot of the evidence for that also comes from looking at the gas flux as well as the deformation. I think it's also been proposed in other parts of the world, for example, at Numuragira and Nyiragongo in the DRC, but I've not seen, I guess, an exactly equivalent data set from that part of the world. So my guess would be that this is something that if you have good enough data, you might be able to observe in lots of other places, but I don't currently know of anywhere else where you've got equivalent observations. I think the Galapagos is particularly easy because the coherence is beautiful and the volcanoes are very close together. And they're also sitting there right near the magma supply by the plume. So a little bit like Hawaii, perhaps you've got more of an opportunity there to look at these deeper variations in supply, which is kind of more challenging in a continental setting. And the other question, I think, was about eruption intensity and how that maybe relates to the magma partitioning. I think the answer is probably that I don't know. I think the most intense eruptions in the Galapagos certainly seem recently to have been associated with these magma flushing events, where you suddenly have an increase in the supply of mafic material from depth. And people have inferred that from looking at the petrology. A lot of Mike Stock's papers kind of are focused on that type of observation, for example, at Fernandina. And I don't know if you'd get an understanding of whether that was kind of more or less likely based on the historical partitioning between the different volcanoes. But I think you might be able to possibly say something about whether you should expect eruptions to be clustered in time. I don't think you can quite do that from the historical record at the moment, but I think it's a question that you perhaps could investigate.
Thank you. Thank you very much.
Great. Well, thanks, Annie. Francisco has his hand up. Francisco, can you unmute yourself and ask your question?
Hi. Yes, I don't have a camera too, so I will only speak. Thanks, Susie, for the talk. Very nice. It was great to see a nice compilation of different SAR results from volcanoes all over the world. And my question is about the method that Edna used to calculate the time average discharge rates based on the backscatter images. I didn't quite understand how you convert the change in backscatter or the backscatter itself to an elevation change. So if you can explain that a little bit with more detail, I would appreciate that. Thank you.
Yeah, so I think the easiest way to think about that is in terms of the number of scatterers. If you imagine a line of range, like scatterers returned along a line of range, and you think about the conversion from a flat surface to one where you have some topography. If you have evenly distributed points with equal scattering potential along a flat line, and then you bend it to the shape of the topography, the spacing of those points is going to change so that you'll have more of them in some pixels as the satellite sees it than you do in other neighboring ones, which is going to result in a difference in brightness, which depends on local slope. So essentially, we work on that assumption and integrate along lines of range. It doesn't work as simply as that, of course, because you have shadows where you have data gaps, and I didn't go into that. But I can send you some more information about it if you like. But so essentially, Edna had to kind of estimate what the difference is across each shadow and then compensate for that. And then the thing that's much harder to deal with is zones of foreshortening, particularly you have a foreshortening right next to a shadow where you end up in a gap. And you have to have some way of bridging that, which we essentially did with smoothing for the most part.
Okay, thank you.
Great. Do we have anyone else online who has a question for Susie? Again, you can either unmute yourself or put it in the chat. I guess if there's a gap here, Susie, I guess one question I have, I really enjoyed all the different topics you covered on. My question was about, you sort of talked about how we could use different satellites to fill in gaps with Sentinel in terms of spatial resolution, but I'm also wondering if you have any sense at the moment about volcanoes that just are not working with automatic processing. I guess you talked about sort of having large deformation rates being more detectable, but I'm just wondering if there's some volcanoes where even at that stage, even large deformation rates might be missed, and if there's any trend we might expect, if Sentinel-1 is missing some volcanoes, or is there some common trend? Is it highly vegetated volcanoes or volcanoes in certain climatic areas, or can we say anything about that at this point?
Yeah, so I think the example, Pedro's work on Sangay is a good example of that, because I think that works better than any of us really expected it to, given that it's highly vegetated, high topography, sits in the tropics. So I think volcanoes in a similar setting tend to be the ones where I think the results are either missing because of incoherence, completely unreliable. So I think it's similar to kind of previous discussions that we've had. There are big gaps in Indonesia. There are gaps over ocean islands, and there are gaps anywhere where you have dense tropical vegetation that extends right up to the summit of the volcano. And I think the Sangay example is good, actually, because although we do have some measurements there, I would argue that actually they're very much incomplete because you only have them above the tree line. So you've only got an indication of things that are happening right inside the volcano's edifice. And if there was a deeper process causing deformation, we really wouldn't have a way of knowing about that from the INSAR. So I think probably volcanoes that are similarly set are the primary places that we're missing. And one thing we've tried to do, what we've been trying to do on and off with like varying success, is get all of the PAL classified A1 volcanoes prioritized for the comet processing. And the success has been patchy. And I think it's primarily for those reasons. I think we're not optimized for places where coherence is very, very spatially limited. So maybe there are some things that you could do. I think processing at full resolution would help potentially, but you're obviously never going to be able to get measurements until SAR arrives and we have L-band everywhere over the dense rainforest.
Great. Well, thanks so much, Susie. If there are no further questions, I think we'll shut it down now and oh, sorry, Annie has another question.
Yes, sorry, a quick question, more anecdotic. You showed at the beginning of your presentation a map with all world volcanoes, and I noticed I saw in France Volcan d'Auvergne, and I was wondering if you already there have been some analysis of SAR data over this Volcan d'Auvergne, and if we see some deformation there. Do you know that?
I can't answer that whether anyone has ever done any analysis. I don't know any of any.
I'm just wondering if there is a risk of eruption in this region.
Also, I know that there are national initiatives in France to process all of the INSAR data nationally. So I kind of suspect that if there had been anything.
Well, as I said, it was anecdotic, but okay. Thank you very much.
Thank you. And thanks again for the invitation.
Great. No, it's good to hear from you, Susie. And this recording should hopefully be online shortly on the AG website. And I'll just say finally, we're not going to have a webinar in December, but we will resume in January. So be on the lookout for that. Have a good day, everybody.
Thanks, Matt.